She said she was recording it, so
yeah, so she should record them. And then can you record it? What happens if you go down to the bottom of your screen to the 3 dots? And then is there an option for you to record it?
It says meeting is being recorded already.
Yeah.
Oh, okay, got it. Yeah. So just, I mean, in case that's helpful, then you just make sure that she posts those recordings.
Yeah.
Yeah. Yeah. Some of these things are going to be tough to do. Yeah. I think that our class is going to be pretty easy to do remotely, but
yeah.
Can't imagine how you do a language remotely.
Yeah, it's just, I don't know. I was really like, I was challenging myself and taking it in general to the school, and now adding this to like online at home. It's just a whole another level of difficulty.
Yeah, well, of course, you can always change to pass-fail if you need to for any of these courses.
Does that mess up like for majors and minors, or?
No, it doesn't. So we're completely waiving all those, rules about majors and minors. The only thing it can mess up for you is your GPA. Like if if you take class pass-fail, it's not going to help your GPA. So if you think you're not going to take it pass-fail.
What would happen if like I have a C in a class and I change it to pass-fail? Does it like help my GPA, or does it stay the same?
Well, so if you change it to pass-fail and you end up passing, it doesn't impact your GPA at all. Whereas if you ended up getting a C, then presumably if your GPA is higher than a 2.0, that has now hurt your GPA. So if you think you're going to get a C, change to pass-fail. Yeah.
Okay, that's what I wanted to know, because that in the email is kind of worded a little weird, for me reading it.
Yeah. But and it's going to be different for different people, right? I mean, I was advising somebody who has a 2.0 GPA, and I'm like, okay, so if you have a 2.0, anything greater than a C is going to pull it up. So if you think you're going to do, if you have a 2.0, then keep your grade at anything greater than a C. But if you have a 3.0, then anything you don't want anything lower than a B is going to pull it down. So.
Do you recall like when are they going to like when's the time zone for allowing us to?
Yeah, I think it's April 18th.
April 18th.
Yeah, it's approximately 2 weeks before the end of the semester, I think.
So
I can test myself and see how bad I'm going and just change it in the last second.
Right. Yeah, you can.
Cool. Take some of the yield pressure off.
Yeah. So we'll give people another minute to get on here. Anybody have any other questions while we're waiting?
So if I'm taking like a language and I change the pass-fail, do I still get the credit for that class?
Absolutely.
I wanted to make sure, because that was my biggest concern. My language is my toughest class, honestly.
Yeah. I mean, we tried to make that policy, pass-fail policy, as beneficial as possible to the students. We're removing all of the, any of the things that kept you from doing pass-fail, whatever. The only thing you got to realize, the only non-benefit to you is that if you change the class to pass-fail, then it just doesn't, it doesn't go into your GPA in any way whatsoever. So
I'd rather risk that than, getting a D and like lowering my GPA.
Absolutely. And that's the whole point, is that for many people, they're going to go, 75% of their classes pass-fail or 100%. But yeah, and that is fine. But, it's like for some people, GPA matters. Like if you're going to go to graduate school, you might care a little bit. In most cases, it's not going to matter even for graduate school, especially because graduate schools are going to know what you went through, right? Everybody in the world is going through this. And some schools are automatically going to all pass-fail. Like you don't even have an option. So
I would hate that.
So yeah. I mean, it's good to give you a choice. I'm not sure why you wouldn't give a student a choice, but and like for my engineers, I say, you need that 3.25 GPA. So if you're taking classes that can help your GPA keep it up at 3.25, then keep your grades. But because that's important. But otherwise, I mean, if you don't have a program that needs a GPA, there's no reason really not to take your classes pass-fail. Let me restate that. If you're taking a class and you can get an A in a class, take the A, right? It's going to help your GPA.
Yeah.
You know,
because like in the material science class I'm in, like I'm taking the prerequisites for it right now. That's like I feel behind in the class, so just having to pass fail is more helpful.
Yeah. I would not. Nobody should feel badly about changing 75 to 100% of your classes pass fail. I mean, if that's the best thing for you, do it. You know, in some cases, like again, if you're going to be a dual degree engineer like Nick, you know, I may have to write a letter when it comes down to it. I mean, they'll recognize the issues, but just say, hey, recognize that there's a semester where nobody in the world had regular classes, and so that's why there's no grades that semester. But I don't think it's going to matter.
Yeah.
Especially this class.
What's that?
Especially the class that I want to do it for.
Yeah. Oh, okay. Yeah. So guys, so lab, I didn't necessarily plan anything. Let me start with, I mean, because I put it all, I hopefully made it relatively clear online. But let me start by entertaining any questions, or if you just want me to do an overview of what we're doing for lab, I'm happy to do that.
Okay.
Any questions to start with? If you didn't read it, that's okay. I mean, it's okay if you haven't read anything yet. Ethan, you got any questions?
Not right at the moment. No.
Okay. So, so again, I don't want to waste your time, but do you guys want me to sort of just do an overview of what today's lab looks like?
Sure.
Yeah.
Okay.
So we know what we're doing.
Yeah. So again, I have no problem doing that. If you go through and read it, you'll probably figure it out yourself. But sometimes it helps just to have me point out some aspects of it. So I'm going to go to presentation mode, and let's make this work. Okay. So I'm now presenting my screen. Okay. So I was just looking at next week's lab. You guys can see next week's lab up here?
Yes.
Okay. Let me go back to this week's lab. So just next week's lab is induction. Don't worry about that. Complex Circuits 2 is today's lab. So let me go back. Complex Circuits 2 is today's lab. And if you haven't done the pre-lab yet, please do it.
I did the wrong one.
Oh, okay. Well, go ahead, go back in and go ahead and do it. Of course, I guess I have to reopen it to accept it. I just realized, but
I did it so long ago, I don't remember what it is.
It was the splitter, the voltage divider.
Mm-hmm.
Ah, okay.
Yeah.
I am just while I'm thinking about it, I'm going in to change. Just for those of you who still need to do it, I just got to change the date that it's due. I'm just going to get rid of the cutoff date. Okay. Okay. So that's back to the lab. Okay. So the pre-lab voltage divider, the point being that if you have a power supply and you have two resistors in series, those resistors share the total voltage. Obviously, we did that in the series circuit. The series resistor lab. And so if you then attach two wires, right? So let's say we've got the 7 ohm and the 3 ohm resistor. That's 10 kilo ohms in series. That would give us a current of, I believe, 1.5 milliamps, because it's kilo ohm. Equals IR. Anyway, so what that means is that the voltage across this resistor, across the smaller resistor, is 4.5 volts, and the voltage across the larger resistor is 11.5 volts. The point being that a voltage divider allows you to then, since the voltage across this resistor is 4.5 volts, that means the voltage between these two wires, which I've attached, is 4.5 volts, and you could use that as a power supply. So we could attach this to something else, and you should get 4.5 volts instead of 15 volts. So a voltage divider takes a fixed voltage and cuts it into pieces, 11.5 and 4.5 in this case. That's why it's called the voltage divider. So in today's lab, I'm going to go to today's lab. You're going to build a voltage divider. So you're going to just build this. But instead of 15 volts, you're going to set the power supply to 9 volts. And you're going to choose 2 resistors so that, okay, so this is where, so that you get 3 volts across one of them. Oh, it says it right there. So you're going to choose your 2 resistors so you get 3 volts across one of them. So if, for example, let's just say I chose a 1,000 ohm resistor on the left and a 1,000 ohm resistor on the right. What would the voltage across this resistor be? It wouldn't be 3 volts. What would it be? If these 2 resistors are the same, it doesn't matter that the value is 1,000. Let's just say that the 2 resistors are equal.
In half, right?
Yes, it would split in half. Exactly, it would split it in half. So if I go 1,000, 1,000, then this is just going to be 4.5 volts.
Mm-hmm.
So in order to split it so that this is 3 and this is 6, so that there's 3 volts across this resistor and 6 volts across this resistor, you've got to have some ratio of resistances that is not 1 to 1 or not,
So
not
2 to 1 ratio then?
I think it's either 2 to 1 or 3 to 2 or something like that.
Yeah.
2 to 1. Yeah, it's 2 to 1. Yeah.
2 to 1. Okay.
Right. 2 to 1. Yeah.
Like 1,000 and a 500, probably.
Yeah, 1,000 and a 500. Exactly. Okay. And you could figure out that therefore it's going to be 3 volts across the 500, because if you did 1,000 and 500, then you'd have 1,500 total in series, and then the current would be 9 over 1,500, 9 volts over 1,500. The current, V equals IR, I equals V over R, 9 over 1,500. And so then the current times the resistor is the voltage through the resistor, right? So if there's 9 over 1,500 is the current, and this resistor is 500, you're going to say, so the current times the resistor, 9 over 1,500, times 500 is 9 over 3. So that's 3. Anyway, I know if I had written this down on the board, it would be more obvious, but you can do the calculation to show that's 3. But yeah, you figure it out. It's 2 to 1. 2 to 1. Okay. So you can choose, it doesn't matter if you choose this resistor to be 2 ohms and this resistor to be 1 ohm, or this resistor to be 1,000 ohms, this resistor to be 500 ohms. It's just 2 to 1. Doesn't matter. But there's the additional manipulation that we're pretending, I'm looking up here, where is it? Oh yeah, that we're pretending that these are 1/4 watt resistors. It means that the maximum power through them is 1/4 watt. The smaller the resistance, the bigger the current. The smaller the resistance, therefore the bigger the power through the resistor. And power, you might remember, you might not, is equal to the current through the resistor times the voltage across the resistor. P equals IV. That's somewhere here in the lab. Just seeing where I've actually, here you go. Power through resistor, P equals IV. So it turns out that if your resistance is too small, then your current is going to be in I and IV is going to be too big. Remember, the voltage is just 3 volts. So if I through that resistor is bigger than some value such that I times V is bigger than 1/4. All right, so let me think about what number that would be. I times V is equal to 1/4. If V is equal to 3 volts, then I is 1/4 over 3, or 1/12.
Okay.
So the current can't be bigger than 1/12 of an amp. Does that make a little bit of sense?
Mm-hmm.
But since this, especially because this is a simulation lab, it doesn't matter. I just calculated it for you. I said this, therefore the smallest resistance you can have is 364 ohms. But you should understand why. I mean, I just want you to understand why. We got to make the 364 ohms is what's going to give us a current no bigger than 1/12 of an amp. You could figure that out, but I wrote it down for you. Now, this is a virtual lab, so it doesn't actually matter if you'd use 2 ohms and 1 ohms, or what's 2 times 364? 728 and 364. It doesn't matter what you use. But we're pretending it's quarter watts. So we're saying the minute to smallest resistor can be 364. Okay. So what you are going to want to do is go ahead and set up this voltage divider in Multisim. Okay. Have any of you tried to log on to Multisim yet?
No, not yet.
Okay.
I'm thinking it's what I used in my electronics class at CVCC.
Very likely, because it's a pretty common program. So Multisim is Multisim Live, or there's a downloadable software, but we're going to use Multisim Live. Multisim.com. You're going to have to sign up for an account. I already have an account. Oh, what's my password? Let's see. Yeah. Okay. So I actually posted on the lab. I posted a video. So I'm not going to go through this all in detail because you should just watch this video. This video is exactly what I'm going to do right now, but I won't go through the whole thing. But you should watch that video. But basically, you got to create an account in Multisim, log on, and create a circuit. And these are all your circuit elements. And there are more because if I like take this resistor and I just single click on it, I can get a resistor, a capacitor, etc. Okay. So I'm going to go ahead and just drag a resistor to the graph paper. I'm going to go ahead and drag a second resistor to the graph paper. And again, I'm doing this quickly because it's in the video. This is my power supply here, sources. These are the ones that we care about, these first 4 in the list on the left. I'm going to grab a power supply, but DC voltage because we're just doing a DC circuit in this right here. I'm going to drop that power supply there. It's in the wrong orientation. I'm going to rotate it. Okay, so now I've got my series circuit without wires. So now you can just go ahead and you can click on the graph paper and you can, whoops, and I moved the graph paper by accident, but I'm just connecting wires between everything. Again, like I said, you can watch the video, you can play with this yourself, but it's pretty easy to do. I'm just clicking in order to connect wires, boom. Okay, there's my series circuit. Now, this is 12 volts. I said we want it to be 9 volts, so I'm just going to go ahead and click on it, and you can change it to 9 volts by sliding this little slider, 6, 9. There we go. Okay. So these are each 1,000 ohms. What did we say the voltage across one of them was going to be if they're 1,000 ohms each?
4.5.
If you said something, I didn't hear it.
4.5.
4.5 volts, yeah, because they're equal, it's 4.5 volts. So how do we tell that? Okay, so here's the thing that you have to do in Multisim. Actually, you probably don't have to do this, but I'm going to ask you to do it, is that we've got to decide where 0 volts is, because unlike in class, when you have a multimeter, and with the multimeter, you have 2 wires that you put across something. Here, we only have a multimeter with a single wire. This is the multimeter here, but it's just a single wire. It probably works just fine. I'm going to go ahead and put it down right here. It doesn't tell me anything yet. But the second wire is where we put our ground. So I'm going to take my ground here, and this is what you're going to have to do, which is different than what we did in class. And I'm going to put the ground down. Whoops, I didn't make a connection there. Come on, make a connection. Sometimes it's a little awkward. Okay, I'll just do it with a wire. Okay, there. All right, you guys can see that the picture, right, of the circuit? Yeah. So the ground is essentially where the other wire for the multimeter is. So what we're doing here, and by the way, we generally, not always, we'll find in electronics lab, 300 level lab, that we don't always put our ground where I did, but we generally put our ground on the negative side of the battery. That's just, and actually what a ground is, this is really, it's an important concept, is that remember that potential energies, we always define our 0 somewhere. The ground is just defining your 0. So we're just saying, oh, here's a 0 voltage, 0 potential energy. And so now V should read 4.5 volts. because it's relative. It's the voltage across this resistor right here, which is the same as the voltage across this resistor. But V is 4.5 volts. But notice that it doesn't read anything. That's because I have to say run. I have to run the circuit, basically turn on the circuit. Turn on the circuit, 4.5 volts. Okay. I'm going to stop the run up here in the upper left-hand corner. And if you actually, I mean, one way to say, oh, so that actually just gives me the voltage across this resistor, which you know is equal to the voltage across this resistor, but that's not always going to be the case. So if I want to measure the voltage across this resistor, one thing I could do is I could take the ground and I could move. Remember, whoops, I have a wire dragging by accident. I could take the ground and put it on this side. So that's again like saying, okay, so this is where my second wire of the multimeter is. I'm going to run it again, 4.5 volts. Okay, got 4.5 volts across each resistor. Okay, stop. But like I said, typically we will leave our ground on the negative side of the battery. Put that back. Okay, so now we said 2 to 1. Give me values. I don't care what resistor values. What should I make the resistor values?
4.
4. Okay, let's make this 4. I'm going to make it 4 ohms. Whoops. I wonder if I can just, type in the value, 4 ohms. Okay, 4 ohms. And so I'm going to make this one 2 ohms. 2, okay, I can type it here. 2 ohms. Okay, 2 to 1. So now because the ground is here and I'm measuring voltage here, I'm measuring the voltage across R1. What should the voltage across R1 be now?
6.
6, right, exactly. It's the bigger one. Yes, 6. So run it. Okay, look at 6. Great. I'm going to stop. I'm going to go ahead and take my ground and put my ground over here. Oops, grab ground. There. Run it. 3. Okay, so the voltage across the 2 ohm resistor is 3. The voltage across the 4 ohm resistor is 6. Okay, so this is our voltage divider. All right, so anyway, so that is the short of it. You are building a voltage divider. And I won't show this, what I'm asking you to do is to go ahead and attach. So we're now pretending that this right here, let me get rid of this here. This is now our 3 volt voltage source, right? Because there's a 3 volt potential difference across here. So I'm asking you to then go ahead and attach a wire. Whoops, a wire. Why am I not getting a wire? Why am I not getting a wire? Let me just put, what happens if I put something here? Okay. Oh, I know why. There we go. Okay. Let me delete this again. Okay. So I'm saying, let's put a wire here. It won't actually let me put a wire to nowhere. But we don't, we're going to put another resistor up here like I had one before. I'm going to put a wire there, and I'm going to put a wire here, and we're going to say the voltage between those 2 wires is 3 volts, and I'm going to attach a resistor in between them. And that's the next part of the lab, is to use R2, the resistor R2, as our 3 volt power supply. Okay, so so anyway, there you go. The second part of the lab is, and you are going to make some measurements. Sorry, once you put this together, you're going to do exactly what I did. You're going to grab this voltage measurer, and you're just going to measure the voltage in various places. That's what you're going to do for the first part of the lab. Second part of the lab is we're going to make an RC circuit like we did last week. Okay, so RC circuit, we're going to put a variable power supply in here, an AC voltage, just like we did last time we met. And RC, we're going to put a C in here instead. I'm not doing it fast, but that's because you can watch the video and see the details, or you can probably figure it out from what I'm doing. So RC circuit, whoops, there we go. Click, connect, RC circuit, click, connect, boom. and connect. I'm actually going to put my ground on the negative side because that's typically where we put our grounds. Okay, there's my RC circuit, just like we had in lab last time we met. And we're going to look at the voltage across the capacitor, just like we did in lab last time we met. So I'm going to go ahead and put my voltage probe right here. So it's measuring the voltage because the ground is here. It's measuring the voltage across the capacitor. Does this make sense so far? Yes. Okay. I said yes for you. So now remember for the RC circuit that we are putting in an AC voltage. Oh, let me actually move my voltage probe. I'm going to move my voltage probe to here so that I measure the voltage just across the output, right? Across my AC voltage. I'm going to go, so now we need an oscilloscope. So the oscilloscope is just the grapher. Going to click grapher. And there's the graph. Actually, go back to my schematic. There's my circuit. And we can actually split the screen so we can still see the circuit and see the graph. So I'm going to go ahead and run. So turn it on. Run, and nothing happens. This is because there's a scaling issue here. My voltage supply is set at 1 volts, but my graph, for some reason, is not in the 1 volt region. So what I'm going to do is scroll down here and hit, okay, there we go. You know, that looks weird, I know, but let me go ahead and run it again. There we go. Okay, there's my oscilloscope, right? It is just showing me the AC voltage from my power supply. I'm going to go ahead and stop that. And now I'm going to move my voltage probe up to where the capacitor is. So now I'm going to, instead of looking at the output from the power supply, I'm looking at the output from the capacitor. I'm going to go ahead and run it again. And it looks exactly the same, which is fine. That's because it should look exactly the same because of the arbitrary values that I chose. That the voltage from the power supply is the same as the voltage across the capacitor because the capacitor is reacting fast enough. It's charging and discharging at the same rate that the power supply is sending out a charge and discharge signal. But the whole point of the second part of the lab is to build this circuit and to see that. But the whole point of the second part of the lab is that if the capacitor cannot keep up, let me go back to my schematic. So in this case, right, where the power supply is charging and discharging the capacitor, the power supply is charging and discharging the capacitor. If the capacitor can't keep up, then that signal will be attenuated. It'll get smaller. Let me just remind you again what that signal looks like. Whoops, grapher. Okay, split. Is that this signal across the capacitor looks exactly the same as the signal out of the power supply. They look exactly the same. But if the capacitor, the RC circuit, can't keep up with the power supply, then the signal across the capacitor is going to look smaller. What do I mean by that? By can't keep up. If it can't charge and discharge, remember there's a time constant, which is R times C. The time constant in this case is 1 micro times 2. The time constant is 2 times 10 to the minus 6 seconds. So if this cycle is, is it faster or slower than? If the period of this sine wave is less than 2.5 seconds, then if the period is less than 2.5 seconds, then this RC circuit can't keep up with it. So I'm not going to say, we're not going to go ahead and measure the period. We're just going to turn up the frequency of the generator. At some point, the RC circuit can't keep up, right? So I'm going to turn up the frequency, let's say by a factor of 10. Let me think about it. If it's 2 microseconds, then it's about 5,000 hertz or 50,000 hertz. I'm not sure which. Let's just go up to 50,000. Let's go to 1,000,000 hertz. All right, so now we're at 1,000,000 hertz. Now RC definitely shouldn't be able to keep up. I'm going to go ahead and play. Oh, there is no voltage probe. I deleted my voltage probe. All right, let's see. There we go. Okay, it's actually squished together. Let me stop. But first thing I want you to notice is that the amplitude is no longer 1 volt. It's actually about 75 millivolts. Let's see, how can I unsquish it? Where's my, where's my, what if I just zoom? No. Voltage? No. That's so weird. Yesterday, when I was doing this, there, on the oscilloscope, there's a way to stretch out your x-axis with a knob that you turn. I'm totally missing it here. It was here somewhere. Not trigger, not edge direction. Plot cursor axes. Very strange. Let's see. But it doesn't matter too much. Hold on a second. The point being, this is a sine wave. It's just really squished together, so you can't see the sine wave. But the amplitude of the sine wave is now at 75 millivolts instead of 1 volt. So the capacitor can't keep up. The signal is smaller. And I'm not sure why I can't find the button that allows me to focus in on that. Sure that with a moment of you guys messing around, you can probably find it. It's definitely not trigger. That's so weird. Yesterday I had it. Anyway, let me turn down the frequency a little bit. Let's go down to 100 kilohertz and see what it looks like. Oh, it's still squishing it too much. Again, it doesn't matter that it's squishing it. You just have to understand that this is a sine wave. It's just the sine wave is so close together, squished in the horizontal axis, that you can't see the sine wave. But now the amplitude again is around 600 millivolts. It's not a full volt because the capacitor can't keep up. Okay, so rather than wasting more of your time trying to figure out where the knob is to show that this is a sine wave, I should just stop messing with that, except that I really want to find it. Let me go ahead and turn this down a little more. 10 kilohertz. Let's go ahead and play it. There, okay. So you can see a little better that it's a sine wave. Let's go ahead and, yeah. Okay. Oh, look, it's back to 1 volt in amplitude. So now it can keep up at 10 kilohertz. Initial conditions. Maximum time. Oh, well. Okay. Anybody have any questions?
Will you post the recording of this?
Yes, I'll post the recording of this. Absolutely. It won't be much different than the recording that I already posted, but absolutely.
Gotcha.
Yeah.
Yeah,
go ahead.
This is a creative lab. Is it not anymore?
It is not anymore. Does it say that? I changed it. Where does it say that?
Should still say creative lab, formal lab due 323.
Oh, right, in Moodle.
Yeah,
I changed it in Moodle. You're right. I changed it on the website. Totally forgot. Yeah. Oh, look, it didn't change. Oh, you know why it didn't change on the website? Because there's something weird about it's caching here. But if you look at this on the website, it will not say creative right there. It'll actually say something else. If I look in Firefox, it'll show me.
Yeah, it doesn't show it.
I just need to prove it to myself now. Hold on. Right.
Yeah, I use Microsoft Edge.
Yeah. For some reason with Chrome, when I have frames, it won't refresh when I make a change. Or it won't. Anyway, okay, so individual for virtual lab. Yes, I will. Thank you for reminding me. I'll change that in Moodle. I will post today's recording in Moodle. And I will change that. Okay. So basically, you are going to go ahead and build those 2 circuits in Multisim. You're going to take a couple of measurements. Once you figure out how to build it, and if you understand what's going on, it's a pretty short lab. But that was the case, right? That was the case with the RC lab, which took everybody 3 or 4 hours. So if you run into problems, you got questions, mess with it a little bit, but then ask me questions. And I can try to guide you. Let me just go ahead and finish reading. I'm not projecting now what I'm reading, but let me just make sure. So the only other thing is that where I was changing the frequency of the function generator that was running the RC circuit, I was changed it from 1 million to 100,000 to 10,000. What I'm asking you to do, the very last thing I ask you to do in the lab, is to adjust that frequency until the voltage across the capacitor is 70% of the voltage of the power supply. 70% of 1 volt is 0.7 volts, right? So you want to adjust that frequency until the voltage across the capacitor is 0.7 volts. I mean, that's, that was just the last thing that I asked you to do. That's just, so therefore you got to go and mess with the frequency until you can figure out that voltage of 0.7. Okay, I don't want to take any more of your time unless you have any questions. That's an overview of today's lab. Ethan, since I can't see you, I can see everybody else, and everybody else is sort of nodding or looking bored. Ethan, are you good?
Yes, I'm all right. I just usually stay quiet if I'm all right. If I don't say anything, if I say something.
Well, I assume so.
This is usually how I am.
Okay. And Dagam's here too. Dagam, you good?
Yeah, I'm good.
All right. Hey, where are you, Dagam? Physically. Where are you located?
Maryland.
Oh, okay.
Yeah. I'm still here.
Okay.
Yeah.
Are you who are you with in Maryland? Is it relatives?
Yeah, I'm with my sister.
Oh, okay. And your parents are back in your home country or no?
Yeah, they're back there.
Okay. And you're staying in the United States?
Yeah, for a while.
Okay, good.
Yeah.
All right. Well, you guys, that's all I got. Unless you have any questions, we don't have to stay on the Google Meet, and you can just send me questions. Or if you want me to get back on the Google Meet, if you're working on it now, I can always do so. Okay. Then we can say goodbye.
Bye.
Bye.
Yeah.
Bye.
Yeah.